Definition of continuity. Before defining continuity formally, we study functions that do not match our intuitive idea of being continuous. This helps us understand the condition required. So for the function f defined as a subset of real number, as C is a domain. So the right hand limit as x to C negative, the right hand limit as x to C positive.
I will start by explaining the different types of discontinuities in a function. There are four main types: removable, jump, infinite, and oscillating discontinuities. Each type shows a different way a graph can be broken or not continuous at a certain point. The first type is removable discontinuity. This happens when there is a hole in a graph. Even though the limit exists, the function value at that point is either undefined or different from the limit. A common example, x squared negative 1, x minus 1. At x equal 1, the denominator becomes 0, creating a hole. This type of discontinuity is called removable because we can fix it by defining the correct value at that point. The second type is jump discontinuity. This occurs when the left hand limit is not equal to the right hand limit. As a result, the graph jumps suddenly from one value to another. In the example shown, the function has two different values before and after x equal 1. So a clear jump happens at the point. The third type is infinite discontinuity. This happens when a function approaches positive or negative infinity at a certain point. It usually occurs when the denominator becomes 0, causing the function to explode towards infinity. A simple example is the function 1 per x, which has a vertical asymptote at x equals 0. On the graph, the values rise or fall without limit near that point. The last type is oscillating discontinuity. This occurs when the function oscillates or wiggles rapidly as it approaches at certain point. Because the values keep changing and never settle, the limit does not exist. A basic example is sin 1 per x. As x approaches 0, the graph oscillates faster and faster, creating a discontinuity.
Okay, so today I'm going to talk about the importance of theorems. In mathematics, some theorems help us understand how continuous function work. The first one is the intermediate value theorem, IVT. It says that if a function is continuous on an interval a, b, then for any value f a and f b, there is a point c between a and b, where fc equal to k. This means a continuous function does not skip any values. For example, if f2 equal 4 and f5 equal 10, then there must be a point between 2 and 5 where fc equals 7. The next one is the extreme value theorem, EVT, which says that if a function is continuous on a, b, then it will have both a maximum and a minimum value. In simple words, a continuous function always reach its highest and lowest points. These two theorems help us understand that continuous functions are smooth and have no breaks or jumps.
I will explain the limit definition of continuity. A function of x is continuous at x equal a if The limit of function of x as x approach a equal the value of the function at a. In simple word, the function has no break, jump or hold at the point. For continuity, at a point, three conditions must be satisfied. 1. Function of a is defined. The function must have a value at x equals a. Second, the limit exists. The left hand and right hand limit must agree. Third, the limit equal function of a. The value you approach must match the actual function value. Next, we have the sum, product and quotient theorems for continuous function. If both function of x and gradient of x are continuous, then first their sum function of x plus gradients of x is also continuous. Number 2, their product function of x multiple gradient of x is continuous. Third, their quotient function of x division gradients of x is continuous as long as gradient of x inequality 0. In short, combining continuous function either by adding, multiplying or dividing keep them continuous. Thank you.
Alright, now I will explain the relationship between limits and continuity. A function is continuous at a point when the limit as x approaches that point is equal to the function's actual value. This requires three things. The limit must be exist, the function value must be defined, and both must be equal. If any one of these conditions does not hold, then the function is considered discontinuous. This relationship is important because limits help us understand the behavior of a function near a particular point.
For the function analysis part, I selected 4 functions, each representing one type of discontinuity. The first function shows removable discontinuity, the second shows jump discontinuity, the third, which is tangent, shows infinite discontinuity, and the last one, sin 1 per x, shows oscillating discontinuity.
Alright, for the function analysis section, we analyze three types of functions. The first one is rational, the second one is piecewise, and the last one is trigonometric. The objective was to identify the points where these functions become discontinuous and then use limits to verify the continuity or discontinuity at those points. Alright, for the rational function, x squared minus 4 per x minus 2, the denominator becomes 0 at x equal to 2. So that is the discontinuity point. When we factorize the numerator, the function simplifies to x plus 2. The limit at x equal to 2 is 4, but the function is undefined at that point, so it is classified as a removable discontinuity. Alright, for piecewise function change formula at x equal to 1, so that's the point we check. The left hand limit and the right hand limit and the function value all equal to 4. Since everything matches, the function is continuous at x minus x equal to 1. There is no discontinuity for this function. And the last one, for the trigonometric function, we choose tan x. The function is undefined wherever cosine equals 0. This happens at pi over 2 plus k pi. At this point, the graph shoots up to infinity or negative infinity. So the discontinuity is classified as an infinite discontinuity. Alright, so to summarize all the findings, the rational function has removable discontinuity xx equal to 2, while the piecewise function is continuous at x equal to 1, and the last one, trigonometric function tan x, has infinite discontinuities at odd multiples of pi over 2.
Okay, so untuk graf nombor 1, H buka kurungan, X tutup kurungan sama dengan tan buka kurungan, X tutup kurungan. Vertical asymptote. So untuk graf yang nombor 2, F buka kurungan, X tutup kurungan sama dengan X kuasa 2 tolak 4 per X tolak 2. Dia berbentuk persilangan panjang, garis panjang tapi tak bersentuh dengan garis tengah-tengah. Okey, untuk yang ketiga pula, X sama dengan pi per 2 tambah K pi. Dia bersilang sama macam yang nombor 2 tapi cuma dia ke bawah sikit.
For the real world application, I choose the example of electricity billing. Electricity bills use a block tariff system, also known as tire pricing, when the cost per unit change once your usage crosses a certain level. This sudden change in rate actually creates a jump discontinuity. In this slide, we can see that the electricity bill can be written as a piecewise function from 0 to 200 kilowatt per hour. The rate is 21.8 cents per kWh. However, now once usage goes above 200 kilowatt per hour, the rate immediately increases to 33.4 cents per kilowatt per hour. This difference in rates before and after the threshold leads to a discontinuity in the cost function. The discontinuity happens because the price changed suddenly at the 200 kilowatt per hour point. This means that the cost from the left side and the cost from the right side are not same at the point. Since the left hand limit and right hand limit are different, this creates a jump discontinuity. This example shows how mathematical concepts also appear in real life situations such as electricity usage and billing.
Okay, so as a function can be understood as a machine. For me, an input goes in is something happen inside and an output comes out. Each new input produce a new output following the rules of the function. We know the function then, given an input, so we can predict the output. Given an output, we can sometimes determine the input. So the expression limits x to a kurungan x sama dengan L means that when x approaches A, the output approaches L. For many simple function, for example like polynomial, rational function with non-zero denominators.
In this part, we analyze whether the electricity tariff function is continuous. The tariff is defined as a piecewise step function where its usage interval has a fixed rate, but the rate changes abruptly at specific thresholds. The total cost increases in jumps rather than smoothly. For instance, when usage increases from 200 to 201 kilowatt per hour, the consumer enters a higher tariff block, causing an immediate rise in total cost. At this point, the left hand limit and the right hand limit are not equal, so the function is not continuous. Thus, the electricity tariff more contains jump discontinuities at every boundary between tariff blocks, which is expected due to its steps-based pricing design.